Welcome to Chapter 16. This is 16.1, all about vector fields. We're going to be talking a lot about vector fields over the course of the rest of this year. Also, we're talking about them secretly a lot in physics. What is a vector field? A vector field is, at its simplest, just some function. In this case, we're sticking to 2D. So it's some vector function of x and y. So what you do is you put a point in, you put an ordered pair in, and you get a vector out. So what it does is it takes literally every point in space and assigns a vector to it. You could imagine, right, think about what the wind speed at every point on Earth is, right? You're going to have a lot of vectors pointing in different directions of different magnitudes. But everywhere in the world, there is some wind speed, even if it's zero. And so we could assign a vector everywhere. Electric fields and magnetic fields are also, and gravitational fields, are also great examples of vector fields. So we're going to be talking a lot about vector fields. And we're going to start in 2D. And the way that we deal with these in 2D is we say that this function, f of x, y, well, it's got to have an I hat component, and it's got to have a j hat component. And in general, these can vary in different ways. So what we usually say is we've got one function, p of x, y, and another function, q of x, y, where p controls the I hat component and q controls the j hat component. Note that these are scalars, and we refer to these as component functions. And they are scalar, p and q are scalars, scalar functions. But in general, we actually usually just write it this way. We'll usually just write pi plus qj. When we get to 3D, we'll add a k hat, but for the moment, we're going to stick to pi and qj. Reminding ourselves that p and q are variables. So let's actually look at an example of one of these. We're going to take this vector field, change colors just to be as colorful as possible. We're going to look at this vector field. We're going to look at f of xy equals negative y I hat plus x j hat. So just as a note, right, if we're doing this, we'd say that the function p is negative y and the function q is positive x. Well, let's get an idea of what this looks like. Let's just plug in some things. If we start with 0, 0, well, we get the vector 0, 0. We get the 0 vector. So I'll just draw that as a dot right here at the origin. We'll come to 1, 0. At 1, 0, we get the vector, okay, well, y is equal to 0, x is equal to 1. We get the vector 0, 1. So if I come out one step here on the x-axis, I end up with this vector. If I go out on the x-axis to 0, I now get a bigger vector. And as I go out 3, 0, 4, 0, I'm going to keep getting these vectors that point in the y direction. Okay. What if we try, say, 0, 1? Well, if I try 0, 1, I get negative 1, 0, which is this vector. And similarly, if I tried 0, 2, I would get this vector. What if I try something that's a little intermediate, right? What if I try 1, 1? Well, if I try 1, 1, I get negative 1, 1. So that's going to be a vector like this. And if I try, say negative 2, 2, I will actually get the vector negative 2, negative 2. So I come here, down, or over here, and I get a vector that points that way. And if I were to keep drawing vectors, what I would actually find is I would get this kind of swirl of vectors. They always kind of circulate in this counterclockwise direction. And as I get farther and farther away from the origin, that swirl gets kind of bigger and bigger. The vectors get longer and longer. But every single vector is going to kind of rotate around the origin in this way. So we're going to look at a bunch of these. I've actually linked on my MCPS, for those of you doing this virtually, which is, I've actually linked on my MCPS a GeoGebra where you can kind of make your own vector fields and take a look at that. So I would suggest that you take a look at that. It's fun to play around with. We're going to see a lot of different types of vector fields. And I do want to note that there's actually one type of vector field that we're going to deal with this year. That is special. And it comes up a lot in physics and in math and in other places. And this is what's called a conservative vector field, also called a gradient field. And you've kind of seen these already before, and this term gradient field might clue you off. You've actually seen one vector field before in this class. You've seen gradients, right? The gradient of f, as you might remember, of some scalar function f is a vector fx, fy. Well, you can evaluate that fx, fy anywhere you want in space. So what we say for these conservative fields is that we're going to say our vector function, pi plus qj, is conservative if and only if, this is a very strong mathematical statement, if and only if, it turns out that there exists some scalar function f, little f, so little f versus big F, such that our vector function is the gradient of our scalar function. And this is why we call them gradient fields. That also means that P would have to be the partial derivative with respect to x, and Q would have to be the partial derivative with respect to y. So if we look, for instance, at at this scalar function, x squared minus y squared, right? If we take its gradient, we get 2x minus 2y. What that means is that the vector field 2xi hat minus 2yj hat is in fact conservative. However, what if we consider this example we had here of negative y plus xj? Well, if we try to test that and see if it's conservative, that would require that if there exists this scalar function, it would require that fx be equal to negative y, which would suggest, by the way, that our original function kind of looked like x times y. Negative xy. But we also have q being equal to x, which implies that our function looks like positive xy. Well, our function can't look like negative xy and positive xy at the same time. So this is not conservative. And in fact, you will often find that these kinds of swirly rotating fields are not conservative. So often fields that look like this are not conservative. If this function does exist, by the way, right, it goes by a special name. The scalar function f of xy is called the potential function of our vector field. And if you're thinking potential, like potential energy or electric potential, you are absolutely right. It does have, in many cases, this physical interpretation, although we'll see other uses for it. So one thing that you will find in physics, for instance, is that voltage is a scalar field. It is, voltage is not a vector, it's just a number. However, the electric field is in fact the negative gradient of voltage. So E fields are conservative fields. Many of the fields we use in real life are conservative. Well, actually, I should be clear about that. Electric fields are, magnetic fields are not. And we'll talk about that a little bit in physics. But in any case, we're going to look at a whole bunch of vector fields, and we're going to examine some ways in class to kind of determine which sorts of fields are conservative and which are not.